For decades, science was convinced it held a reliable narrative for how the universe evolved. A beginning known as the Big Bang, followed by a slow accumulation of structure, chaotic little galaxies first, order arriving much later, an expansion driven smoothly by dark energy. It wasn't a perfect model, but it was consistent. Then came the James Webb Space Telescope. It didn't send back theories or simulations. It sent back observations. Tens of thousands of ancient galaxies seen in unprecedented detail. And suddenly, the numbers stopped adding up. The shapes appeared too mature, the structures far too organized. At a time when the universe should have still been learning how to exist, it looked disturbingly well assembled. Even more unsettling, large statistical studies suggested that what we interpret as cosmic expansion might not be what we think it is at all. Dark energy itself started behaving strangely. Time, age, and even direction began to feel less universal than we had been taught. This isn't a story about a single anomaly. It is about a pattern, and it begins with a galaxy that simply shouldn't be there. When scientists published a new paper in Nature Astronomy based on deep observations from the James Webb Space Telescope, one object immediately stood out: a massive disk galaxy in the very early universe. It was so large and so structured that it forced researchers to stop cold. They called it the Big Wheel. Light from this galaxy traveled over 12 billion years to reach us. This means Webb was observing it as it existed within the first 2 billion years after the Big Bang, when the universe was only about 15% of its current age. Under the standard cosmological model, galaxies at this stage are supposed to be small, irregular, and poorly defined, still assembling from chaotic clumps of matter. But the Big Wheel didn't fit that picture at all. Webb's detailed view showed it is comparable in rotational speed and size to the largest super-spiral galaxies in the universe today. It is roughly 3 times larger than other galaxies from the same epoch and ranks among the most massive ever seen, so early in cosmic history. This was not a minor deviation. It was a direct contradiction. A galaxy boasting a well-defined disk, organized rotation, and enormous mass appearing at a time when the universe should not have been capable of producing it. And the most troubling part was this: the Big Wheel was not alone. As Webb continued to survey the early universe, the problem deepened. The Big Wheel was not an isolated cosmic fluke. Multiple massive, well-developed galaxies were discovered in that same early period. Each discovery added weight to the same uncomfortable conclusion: the early universe was far more structured than our models predict. According to the standard cosmological framework, early galaxies should lack rotational stability and clear shapes. Yet, Webb kept finding systems that looked mature, organized, and dynamically settled far too soon. The Big Wheel merely stood out because it was the largest among them, the most extreme example of a pattern that refused to go away. This forced scientists to confront a difficult reality. Either galaxies formed much faster and more efficiently than current physics allows, or our understanding of cosmic evolution is missing something fundamental. When researchers analyzed tens of thousands of early galaxies detected by Webb, the statistics confirmed that these anomalies were not rare. They were systematic. The early universe, once imagined as primitive and chaotic, was revealing itself to be unexpectedly sophisticated. And if galaxies could reach this level of organization so early, then the timeline we use to describe the universe's growth might be deeply flawed. The James Webb Telescope didn't just find a strange galaxy. It exposed a crack in the foundation of how we think structure emerges in the cosmos. As scientists expanded their analysis beyond individual objects to study Webb's data at scale, the problem stopped being visual and became mathematical. Researchers examined roughly 30,000 early galaxies detected by the James Webb Space Telescope and found patterns that did not align with expectations derived from the Big Bang model. The numbers simply did not match what theory predicts for a universe at that stage of evolution. According to the standard picture, cosmic structure should emerge gradually. Matter should clump slowly, galaxies should grow over time, and large organized systems should be rare in the early universe. But Webb's massive statistical studies suggested otherwise. The distribution, maturity, and size of these early galaxies implied that cosmic evolution may not be following the timeline scientists have relied on for decades. This discrepancy triggered a deeper concern. If we are observing a single universe, the numbers describing its expansion and structure formation should be internally consistent. But they were not. Researchers openly admitted that something appeared to be missing from the standard model, something not accounted for by dark matter or dark energy as currently understood. The implication was unsettling. If the numbers are wrong, the story they support might also be wrong. As these inconsistencies accumulated, scientists began asking questions once considered almost untouchable. Could it be that the Big Bang, as we currently understand it, is not the complete explanation for the origin of the universe? The document makes it clear that this is not fringe speculation, but a serious discussion emerging from respected researchers confronted with Webb's data. The issue is not whether the universe had a beginning, but whether the standard narrative accurately describes what happened next. If galaxies formed faster, grew larger, and organized themselves earlier than predicted, then the assumptions underlying cosmic evolution may be incomplete or fundamentally flawed. This forces scientists to consider the possibility that there is an unknown physical component influencing the universe, something beyond the dark energy and dark matter already built into the model. The James Webb Telescope has not provided an alternative origin theory. What it has done is remove the comfort of certainty by revealing a universe whose early behavior does not align with the Big Bang's expected outcomes. Webb has pushed cosmology into a state of re-examination. The origin story we rely on may still hold elements of truth, but it no longer feels sufficient on its own. And once the origin is questioned, every conclusion built on top of it becomes unstable. For decades, dark energy has been the invisible pillar holding modern cosmology together. In 1998, astronomers discovered that the expansion of the universe was not slowing down under gravity as expected, but accelerating. No one knew why. The force driving this acceleration was unknown. So, it was given a name that openly admitted that ignorance, dark energy. From that moment on, cosmologists assumed one crucial thing. Whatever dark energy was, it behaved the same everywhere and at all times, acting as a constant that allowed scientists to calculate the universe's age and trace its evolution. But the document makes clear that this assumption is now under serious threat. New observations, including those involving the James Webb Space Telescope and large-scale galaxy surveys, have revealed hints that dark energy may not be constant at all. When researchers first noticed subtle signs that its influence might have changed over time, many believed it was simply a blip in the data, a statistical fluctuation that would disappear with better measurements. It didn't. After more than a year of additional observations and extensive testing, scientists confirmed that dark energy is behaving far more strangely than expected. Even cautious and highly respected researchers involved in the studies began expressing confidence that these results were not caused by unknown errors or overlooked effects. The force that was supposed to be the most stable element of cosmology was suddenly becoming unpredictable. As the mystery deepened, another long-standing problem grew impossible to ignore. The expansion rate of a universe appears to change depending on how it is measured. When scientists analyze the cosmic microwave background, they obtain one value for how fast the universe is expanding. But when they calculate the expansion rate using predictions from the standard cosmological model and observations of galaxies, they get a completely different value. This mismatch is known as the Hubble tension, and it suggests that something fundamental is wrong. According to the standard model, dark energy drives expansion at a constant rate everywhere, meaning all parts of the universe should share a single cosmic timeline. But recent discoveries challenge this assumption. Observations indicate that dark energy may have behaved differently in the early universe compared to today. If true, this would mean that different regions of the universe could have experienced accelerated expansion at different times, altering how old they appear to us. Now, This is not a small correction. It strikes at the idea that the universe has one unified age and one universal history. If dark energy changes over time or behaves differently depending on context, then our methods for calculating the universe's age and evolution become unreliable. The James Webb Telescope has added weight to this crisis by revealing inconsistencies that cannot be ignored. Dark energy, once treated as a steady background force, now looks like a moving target. And when the force governing cosmic expansion becomes uncertain, the entire framework of modern cosmology begins to wobble. To explain the growing list of contradictions, scientists have begun exploring models that challenge one of the most basic assumptions in cosmology, that time flows the same everywhere. The document introduces timescape cosmology, a radical framework proposing that the apparent acceleration of the universe is not driven by dark energy at all, but by differences in how time passes across cosmic structures. In this model, regions of space with high matter density, such as galaxies and clusters, experience time more slowly than vast cosmic voids where matter is scarce. An atomic clock inside a galaxy could tick up to a third slower than an identical clock placed in an almost empty region of space. Over billions of years, these differences accumulate dramatically. Because time passes faster in cosmic voids, those regions have effectively experienced more expansion. As voids grow larger and come to dominate the volume of the universe, their faster expansion creates the illusion that the entire universe is accelerating. In this scenario, dark energy is not required. The expansion we observe is a consequence of time itself flowing unevenly across the cosmos. This idea directly challenges the assumption that the universe has a single universal age. Instead, the age of a universe would depend on where you are. In dense regions, the universe would appear younger. In vast voids, it could be billions of years older. The James Webb Telescope's observations, combined with large galaxy surveys, have given this model renewed attention because they expose cracks that the standard model struggles to explain. The document then introduces an observation that pushes this crisis even further. In a recent study of roughly 30,000 galaxies observed by the James Webb Space Telescope, scientists found something profoundly unexpected. Most of these galaxies appear to be rotating in the same direction. According to the Big Bang theory, the universe should have formed chaotically with galaxies spinning randomly. There is no reason for large-scale alignment. Yet, the data suggests otherwise. This unexpected uniformity implies that the universe may have begun with an initial spin, something current cosmological theories do not account for. This finding opens the door to even more radical possibilities. Some scientists are now considering whether the universe itself could have formed inside a rotating black hole, an idea known as the black hole universe hypothesis. While speculative, it offers a framework in which a preferred direction and large-scale rotation could naturally emerge. Taken together, uneven time flow, the dominance of cosmic voids, and large-scale rotational alignment paint a picture of a universe far stranger than the one described by traditional models. The James Webb Telescope did not provide definitive answers, but forced cosmology to confront questions that were once unthinkable. If time does not flow uniformly and the universe has a built-in direction, then the foundations of modern cosmology may need to be rewritten from the ground up. The James Webb Space Telescope did not break science by making a mistake. It broke science by doing exactly what it was built to do. It looked deeper, earlier, and with more clarity than any instrument before it. And what it found did not behave the way our theories said it should. A universe that was supposed to be young and chaotic revealed galaxies that were massive, ordered, and mature far too soon. Numbers that should have matched refused to align. The origin story we rely on began to feel incomplete. Then dark energy, the invisible force holding the entire framework together, stopped acting like a constant and started behaving differently depending on when and how we observe it. Time itself became suspect. Age stopped being universal. Expansion stopped being simple. And when scientists tried to patch these cracks, They were forced to consider ideas that once lived on the fringes. That cosmic acceleration might be an illusion created by uneven time flow. That vast voids age faster than dense regions. That the universe may not share a single timeline. That it might even have begun with a preferred direction, a rotation written into its very structure. None of this means that science has failed. It means it has reached a boundary, a point where observation has outpaced explanation. The James Webb Telescope did not deliver a replacement theory. It delivered something far more disruptive, proof that the universe is not obligated to follow the models we built to describe it. This is how scientific revolutions begin, not with answers, but with contradictions that refuse to go away, with data so precise that it forces us to abandon comfortable assumptions, with the realization that what we thought was settled was only provisional. The universe has not changed. Our understanding of it has. And the most unsettling part is this. We are likely not witnessing the end of the story, but the beginning of a new one. One where time, origin, expansion, and even the age of the universe itself must be reconsidered. James Webb didn't just show us the early universe. It showed us how much we still don't understand about the one we live in. I'd love to hear what you think about this, so drop a comment below. If you enjoyed our conversation today, please share this video and subscribe to help the channel grow. Every bit of support counts.